Today's lecture is going to be on certain special areas of capital budgeting. We have started speaking about capital budgeting for the last couple of lectures, and now we will be talking in some detail about certain special cases where the net present value and IRR are a bit more difficult to calculate. So it's hoped that by going over some numerical examples, the concepts will become clearer to you. First thing that I would like to do is go over some of the material related to capital budgeting that we talked about in the previous lecture. We mentioned that here we are talking about the area of capital budgeting as it relates to projects, and by this we mean investments in real assets. Real assets would include fixed assets such as land and property, machinery and equipment. We also mentioned that the major limitation or difficulty in net present value calculation is in your ability to estimate or forecast the cash flows. That exercise by itself has perhaps the largest room for error. So you need to spend some time in trying to make sure that your cash flow forecasts are accurate. We have a simple formula for calculating the cash flow statements. The way we define net incremental after-tax cash flows for the purposes of this course is basically in terms of the net operating income, which you would pick from the pro forma P&L or income statement, and added to that you would include the depreciation, which was a non-cash expense. You would add any tax savings from the increase in depreciation, which is separate from the depreciation itself. You would add or subtract any amount of tax that would be due because you may have sold an existing or old equipment over or below its book value. And finally, you would include whatever incremental net working capital is required for the particular project. The things that we have left out in this estimate of net after-tax incremental cash flows are certain incidental cash flows that we talked about earlier, and those were your opportunity costs, your externalities, and your sunken costs. The next thing that we had spoken about earlier was the two major criteria that we use in capital budgeting. And they are net present value, or NPV, and IRR, or internal rate of return. We mentioned that the most important criteria is net present value, because that has a direct link to the shareholders' wealth maximization, which we spoke about at the beginning of this course as being the objective in financial management. I should mention here that the area that we are talking about, capital budgeting, is covered in chapters 9 and 10 of the 8th edition of Financial Management by Brigham and Gapensky. So I urge you to go through these chapters in case you're having difficulty understanding these concepts. We spoke about and we introduced some of the difficulties that you can face in net present value and IRR calculations. I'd like to go over those special cases in detail today by way of certain numerical examples and explanations. So the first difficult area that we covered related to IRR was the case of multiple IRRs. The case where you can have a certain project with certain cash flows that are not normal, and when you try to compute the IRR, you can have more than one answer. This is the case where you have more than one sign change taking place in your cash flow diagram. When we talk about a sign change, we're saying when you have two adjacent arrows, that one of them is downward pointing and the other one is upward pointing. And when they are adjacent in periods of time, we would call that a sign change. In general, our cash flow diagram begins with a downward pointing arrow to signify the cash outflow for investment. And it is followed by a series of upward pointing arrows that designate net incoming cash during the life of the project. However, if during the life of this project, at any one period in time or more, you have a net cash outflow or a downward pointing arrow, then that would be a second sign change. And you can expect to have multiple answers for IRR. Now, in this particular case, using the net present value equation and setting it equal to 0 to calculate IRR will give you two answers, and both of them would be wrong. So what do we do? The alternative is to use what we call the modified IRR approach, or MIRR. What is the logic of MIRR? Basically, what you do is, instead of looking at the net cash flows at each period in time, you look at the cash inflows and the cash outflows separately for each period in time. Then you lump the incoming cash flows and you compound them to the termination date or the ending point of this project, and you lump all of the cash outflows during the life and you discount them to the present. So you have outflows being discounted to the present and inflows being compounded to the future date or the termination date of the project. And then the MIRR represents the discount rate which will equate or make equal the future value of the cash inflows to the present value of the cash outflows. And there was a formula that I had mentioned earlier, and that is 1 plus MIRR raised to the power n is equal to the sum of the cash inflows multiplied by the compound factor, which is 1 plus I raised to the power n minus t, all divided by the sum of the cash outflows divided by the discount factor, which is 1 plus I raised to the power t. So, using this equation, we can compute the modified internal rate of return, which can give us an answer which is entirely different from the two values that you obtained using the simple IRR approach. Now, let's move on and take a look at a simple numerical example that will clarify the calculation. We will take a look at a project that has a cash flow pattern as follows. In this project, you will make an initial investment of 100 rupees. After 1 year, you will have a net positive cash inflow of 500 rupees. And after 2 years, you will have a net cash outflow of 500 rupees. Now, if you use your standard net present value equation to calculate the IRR, you would come up with two answers. One of them is 38% and the other one is 260%. And we came to this conclusion in the previous lecture. Now, both of these answers are incorrect. So, we will use the modified IRR approach to calculate the actual IRR for this project. So, if we plug in the different variables in the MIRR equation, we would have an equation that looks something like this: 1 plus MIRR raised to the power 2. Why 2? Because the life of this project is 2 years, is equal to the sum of the cash inflows multiplied by the compound factor. That is equal to 500 multiplied by 1.1 raised to the power 1. Why 1? Because the compounding of the cash inflows takes place from the point at which the cash inflow occurs to the termination date of the project. And in this case, the cash inflow takes place at year 1, and the project life is 2 years, so 2 minus 1 is 1, and that represents the exponent in the numerator. Why did we talk about 1.1 as the base in the compound factor? Well, because remember we mentioned that the compound factor is equal to 1 plus I raised to the power n minus t, and I over here represents the rate at which your money can be safely reinvested. And the safest figure that we can pick is that of a risk-free rate of return, which we spoke about earlier. In the case of Pakistan, a safe number to pick would be 10%, because that comes close to the kind of return you can expect if you deposit your money in a bank account. If you want to be even more safe, you could use the risk-free rate of return of the government of Pakistan T-bills, which could vary anywhere between 7 to 12%. Now, to complete this equation, in the denominator, we have to quantify the cash outflows. For this particular example, the cash outflows would be 100, which is the cash flow taking place initially in the present period, plus 500 divided by 1.1 squared. This is because the cash outflow is taking place in the second year, and that amount is 500. So we would divide 500 by 1.1 squared. The final answer that you get if you solve this equation for MIRR would be 3.44%. Now, you'll note that this 3.44% is entirely different from the answers we got using simple IRR, which were 38% and 260%. However, this modified IRR technique, or MIRR, gives you the best answer possible. Now, the next special area or complicated aspect of capital budgeting that we began talking about in the previous lecture was the case where you're comparing projects which have different lifespans. In that case, supposing that you have two projects, both with different lifespans, it is not entirely accurate to calculate the NPVs in the simple manner and to compare them and to pick the project with the higher NPV. Why is that? Because you are comparing a certain project with limited cash flows for a short period of time to another project that has cash flows extending over a long period of time. So, we have two approaches that we mentioned in order to handle this problem. One of them is the common life approach, and the other one is the effective annual annuity approach, or the EAA approach. In the case of the common life approach, the idea is quite simple. You need to bring all the projects to the same length of time. In other words, you want to convert all the projects to an identical lifespan. How do you do that? By finding the least common multiple for the lives of the different projects. In other words, if you're comparing two projects, one which has a life of 4 years and another which has a life of 5 years, then what would be the least common multiple? It would be 20 years. And so you would have to take each one of those projects, sketch their cash flow diagrams, and replicate the cash flows for each of the projects such that they fit in a certain exact number of times in 20 years. In the case of the project that has a life of 4 years, you can replicate the cash flows 5 times in a period of 20 years. In the case of a project with a life of 5 years, you can replicate that cash flow cycle 4 times exactly in 20 years. Then you would need to calculate the NPVs for both of these projects with their new common life, and that will allow you to decide which project has the higher NPV, and you would pick that project as the better one. We will do a numerical example in a moment to clarify what I just mentioned. The other approach was the annuity approach, and in this case, our logic is to find out that for a particular project of a limited life, giving you a certain net present value calculated a simple way, what kind of an annuity can you come up with that would yield the same net present value? Now, when you've come up with that answer, what kind of annuity, in other words, what kind of a cash inflow per year will give you a certain net present value that you've already calculated, you can then compare that annual annuity of that project to the annual annuity that you've calculated for the other project, and you would be safe in doing so because you are comparing two things that are similar. You are comparing the cash flows then of two projects, both of which are taking place in a period of 1 year only. So that is the logic behind the effective annual annuity approach. You can also convert the cash flows of every project to a perpetuity, which is infinite, and then compare what the NPVs are like of the different projects. That would also be correct. Why? Because an infinite lifespan for a different number of projects is identical. Now, let's try to understand numerically what I just mentioned to you. We'll do a simple example and a numerical whereby we will take a look at two projects with two different cash flows and different lifespans. Project A has a simple cash flow. In the present period of time, or year 0, you invest 100 rupees. That is a cash outflow or a downward pointing arrow. And then, at the end of the first year, you have a net cash inflow of 200 rupees, represented by an upward pointing arrow. The second project, Project B, has the following cash flow: an initial investment of 200 rupees taking place at year 0, then a net cash inflow of 200 rupees taking place at the end of the first year, and then another net inflow of cash taking place at the end of the second year of 200 rupees again. So you will note that project A has a life of 1 year and project B has a life of 2 years. Now, if you use our old and simple technique of calculating the NPV without any modifications, then the net present value for project A will come out to be 82 rupees. And if you calculate it in detail, you can say that the net present value of A is equal to minus 100 plus 200 divided by 1.1. Again, we'll keep our net present value calculation simple by using a required rate of return, or I, of 10%. If you calculate the simple net present value of project B, that would be equal to minus 200 plus 200 divided by 1.1 plus 200 divided by 1.1 squared. And the answer for the NPV for project B would be 147 rupees plus. So, if we use a simple NPV approach, the answer is simple. Project B is clearly better because it has a higher NPV, and you would decide to invest in project B. But, as I mentioned earlier on, here we are comparing apples to oranges, because one project has a life of 1 year and the other project has a life of 2 years. So let's try the common life approach to equate these projects, put them on the same lifespan, and then calculate their NPVs and compare them. जब हम कॉमन लाइफ अप्रोच इस्तेमाल करते हैं एनपीवीज को कैलकुलेट करने के लिए, तो हमें सबसे पहले एक कॉमन लाइफ स्पैन निकालना होगा इन दो प्रोजेक्ट्स का. एक प्रोजेक्ट का लाइफ स्पैन 1 साल है और दूसरे प्रोजेक्ट का लाइफ स्पैन 2 साल. लिहाजा इनका लीस्ट कॉमन मल्टीपल 2 साल बनता है, बिकॉज 1 times 2 is equal to 2. This example is quite simple, because in this case all we need to do is repeat or replicate the cash flow for project A twice, because that will exactly cover the 2-year period. When you take a look at the slide, you will see that the cash flow diagram of project A has been repeated again over the time period between 1 and 2 years, so that you will see a downward pointing arrow in year 0 representing the 100 rupees of cash outflow, followed by the 200 rupees of cash inflow shown by an upward pointing arrow at the end of year 1. And now you would repeat this cycle over year 1 and year 2. So you would have a downward pointing arrow in year 2 representing the 100 rupees of cash outflow, and then again you would show a upward pointing arrow to represent the cash inflow of 200 rupees taking place at the end of year 2. You can simplify this diagram because you have 2 arrows at one point in time, which is year 1. You have an upward pointing arrow of 200 rupees and a downward pointing arrow of 100 rupees. So the net cash flow for this particular point in time, year 1, is a net cash inflow of 100 rupees, which you can show by a upward pointing arrow. This is the case for project A. And this is the complicated one, because project B is unchanged. The life of project B was originally 2 years, और क्योंकि project B की life पहले से ही 2 साल थी, हमें उसको मजीद चेंज नहीं करना पड़ेगा. लिहाजा अब हम project A की net present value उसके नए कैश फ्लो डायग्राम के बेसिस पे कैलकुलेट कर सकते हैं. जब हम ये कैलकुलेशन करते हैं तो प्रोजेक्ट ए की नेट प्रेजेंट वैल्यू is equal to minus 100 plus 100 divided by 1.1 plus 200 divided by 1.1 squared. And the answer that we get for project A's modified net present value according to the common life approach is plus 156 rupees. Now you will note that the net present value of project B is unchanged at 147 rupees. So what has happened now? Our conclusion has changed. पहले हमने कहा था कि प्रोजेक्ट बी बेहतर है जब हम सिंपल एनपीवी कैलकुलेशन कर रहे थे, और अब जबकि हमने एक्यूरेट कॉमन लाइफ बेसिस के ऊपर नेट प्रेजेंट वैल्यूज कैलकुलेट की हैं, तो हमारा नतीजा फर्क है, वो ये कि प्रोजेक्ट ए बेहतर है. एंड इन फैक्ट दिस इज करेक्ट. प्रोजेक्ट ए इज इन फैक्ट बेटर. And when you compare the net present values, then you can see that the net present value of A at 156 rupees is higher than the net present value of B, which is 147 rupees. Also note how the net present value of A increased from 82 rupees to 156 rupees. It almost doubled. Why? Because you doubled the lifespan of this project. So this is the common life approach to handling and comparing two different projects which have different lifespans. The next thing that I'd like to talk about is the effective annual annuity approach, or the EAA approach, to solving the problem of comparing projects with different lifespans. जैसे कि मैंने पहले जिक्र किया, इफेक्टिव एनुअल एन्युटी अप्रोच में हम ये सवाल पूछ रहे हैं कि जो सिंपल नेट प्रेजेंट वैल्यूज हमने पहले कैलकुलेट की थी प्रोजेक्ट्स के लिए, वो हम एक एन्युटी स्ट्रीम से कैसे अचीव कर सकते हैं. लिहाजा यहां पे हम एक बैक कैलकुलेशन कर रहे हैं कि हमें नेट प्रेजेंट वैल्यू तो मालूम है, लेकिन ये कौन सी एन्युटी स्ट्रीम को रिप्रेजेंट कर रही है उस लाइफ स्पैन में जो लाइफ स्पैन प्रोजेक्ट का है. और फिर हम ये करेंगे कि हम जो एनुअल एन्युटी वैल्यू है एक प्रोजेक्ट की, वो दूसरे प्रोजेक्ट की एनुअल एन्युटी वैल्यू से कंपेयर करेंगे. और ये एक सेंसिबल कंपैरिजन होगा, वो इसलिए क्योंकि ये एक साल तक महदूद है. लिहाजा इस कंपैरिजन का लाइफ स्पैन जो है वो एक साल का पीरियड होगा दोनों केसेस में. आइए अब एक न्यूमेरिकल एग्जाम्पल करते हैं इस कॉन्सेप्ट को क्लैरिफाई करने के लिए. जस्ट टू रिमाइंड यू द वे वी विल calculate the effective annual annuity is simply by multiplying the simple value of the NPV, which you calculated right at the beginning, by what is known as the EAA factor, or the effective annual annuity factor. इस फैक्टर को आप याद रखने की कोशिश कीजिएगा. This is equal to 1 plus I raised to the power n, all divided by 1 plus I raised to the power n minus 1. Now, in this formula, I represents the required rate of return and n represents the actual life of the project. So, if we talk about the same example that we looked at in the common life case, Project A and Project B, with Project A having a life of 1 year and Project B having a life of 2 years, then what is the value of the effective annual annuity factor for Project A? That is equal to 1.1 divided by 1.1 minus 1. And that is equal to 11. In the case of project B, the EAA factor is equal to 1.1 squared, all divided by 1.1 squared minus 1. And that is equal to 5.76. Now we can calculate what the effective annual annuity for each project will be. For project A, that will be equal to the net present value of A, the simple net present value of A, multiplied by the effective annual annuity factor for A. So that is equal to 82, which was the net present value, multiplied by 11, which is the EAA factor. And that gives us an effective annual annuity for project A equal to 902 rupees plus or positive. Similarly, in the case of project B, which had a life of 2 years and an effective annual annuity factor of 5.76, the annuity value is equal to 147, which was its simple net present value, multiplied by 5.76. And that is equal to 847 rupees plus. So, now you can compare the net present values of the two projects in the effective annual annuity form, and you come up with the same conclusion that you came up with when we used the common life approach. And that conclusion is that project A is better. Why? Because the annuity value for project A comes to 902 rupees, and the annuity value for project B comes to 847 rupees. So, the conclusion that you come to using the common life approach or the effective annual annuity approach is the same. But of course, the numbers are different. And why are the numbers different? Because for common life, you're calculating the net present value over a common lifespan. Whereas for effective annual annuity, you are calculating the annuity value or the constant cash flow for only 1 year. So naturally, you can't expect the annuity value to be identical to the net present value. However, the conclusion that you come to is consistent. Let me just give you a practical angle on this issue of comparing different projects or investments with different lifespans. अमूमन कंपनीज और इंडिविजुअल्स को इस फैसले का सामना करना पड़ता है. मिसाल के तौर पे अगर कोई भी दर्जी की दुकान या कोई फैशन बुटीक हो जिसको सिलाई की मशीनें लेनी है, उसको ये फैसला करना होगा कि आया कि ऐसी मशीन ली जाए जो पायदार है और जो काफी अरसा चलेगी, हो सकता है कि 8 से 10 साल चले, या कि कोई ऐसी सिलाई की मशीन ले जिसकी लाइफ स्पैन जो है वो सिर्फ 2 या 3 साल हो. सो देयर आर एडवांटेजेस एंड डिसएडवांटेजेस एसोसिएटेड विद लॉन्ग एंड शॉर्ट लाइव्स फॉर सर्टेन प्रोजेक्ट्स. अगर किसी भी प्रोजेक्ट की लंबी जिंदगी है तो उसके नुकसानात और उसके फायदे भी हैं. फॉर एग्जाम्पल, when we talk about a project or a fixed asset like a machine such as a sewing machine or a printing machine, one that has a long life of maybe 8 or 10 years, then of course the advantage is that you have a predictable forecast for the kind of cash flows that you can expect from this asset. The disadvantage is that you will miss out on the opportunity to extract full value from this asset and replace it in a short period of time. Why is it an advantage to do this? Well, simply because बहुत सी इक्विपमेंट और बहुत सी मशीनरीज में टेक्नोलॉजी इतनी तेजी से बदलती है कि आप फायदे में रहते हैं अगर आप उस इक्विपमेंट को या उस मशीनरी को जल्द अज जल्द तब्दील कर सकें. सो फॉर एग्जाम्पल, इन द केस ऑफ a computer or computer hardware, it's oftentimes to your advantage to be able to reinvest in computer hardware within a relatively short period of time, like 2 or 3 years, because the technology is changing at such a fast pace. The advantage you have from reinvestment in a short period of time is that you can generate better quality at a quicker speed and possibly also at lower costs. So when we spoke earlier on about options and option values, then this is a kind of a hidden option value, and that is in the form of a project with a short lifespan. It gives you the opportunity to replace the asset with another one that is superior in quality and allows you to cut down costs and improve the speed of work. Now, in the case of a project which has a short lifespan, then of course the advantage, as I mentioned, is that you can replace the equipment or machinery in a short period of time with a newer one that might be superior in quality and will allow you to maintain your competitiveness. The disadvantage of projects with very short lifespans is that your cash flow is not predictable. In other words, if the life of the project is only 2 years, then you don't know what kind of cash flows to expect after the 2 years are over. What will you do with your money after 2 years if you cannot invest it in a project that will give you a return in the form of IRR or NPV to match the return that this project was giving? कहने का मकसद यह है कि अगर आपके प्रोजेक्ट का लाइफ स्पैन बहुत छोटा है तो उस लाइफ स्पैन मुकम्मल होने के बाद आप अपने सरमाए के साथ क्या करेंगे, उसको कहां री इन्वेस्ट करेंगे. और अगर आपके पास उस जितना अच्छा या उससे बेहतर कोई प्रोजेक्ट नहीं है तो आपको अपना पैसा हो सकता है कि किसी भी पीएलएस सेविंग्स अकाउंट में डालना पड़े जिसमें आपको सिर्फ 9 या 10% सालाना मिलेगा. सो दिस इज द डिसएडवांटेज ऑफ ए प्रोजेक्ट विद अ वेरी शॉर्ट लाइफ स्पैन. Again, both of these kind of situations can be addressed using either the common life method or the effective annual annuity method for calculating the net present value. यहां पे मैं एक वक्फा लेना चाहता हूं और इस चीज की अहमियत आपको बताना चाहता हूं कि हम फिलहाल एक बहुत ही आइडियलाइज सेंस में कैपिटल बजटिंग के बारे में बात करते आए हैं. वी हैव बीन टॉकिंग इन ए वेरी वेरी आइडियल सेंस बिकॉज वी हैव टोटली ignored a very, very important and practical part of capital budgeting. And that fact is that money is limited. The money that a company or that you have is limited. And you can only invest in projects that have investments less than or equal to the amount of money you have. Why is money limited? Well, it's limited because the amount of equity or debt that you have in the company is limited. You might have limited resources for getting financing or borrowed funds. So, not only are your financial resources limited, but you also cannot undertake certain projects because you don't have the management or the workforce that is skilled enough to undertake certain projects. These projects typically are high-tech or research and development intensive projects. Even though their NPV calculations may show that they are the best projects and their NPVs are very high, you cannot undertake them because you don't have perhaps the financial resources and the human resources to undertake such projects. You can argue that certain companies may have access to borrowing or to financing, but they choose not to borrow money either for religious reasons or possibly because they have a certain fear of debt and repayment of interest. Because debt and repayment of interest, as we'll talk about later, brings on risk. And many companies and many managers choose not to take on that risk. So there are many reasons why, even after all of these calculations of net present value and IRR, you may decide that you cannot undertake a particular project. Let me stop the new material for this particular lecture right here and recap some of the concepts and special cases related to IRR and net present value that we have spoken about. The first one was multiple IRR. This case arises when you have more than one sign change taking place on the cash flow diagram. That means that there are more than one points in the cash flow diagram where you are moving from a downward pointing arrow to an upward pointing arrow, or vice versa, in adjacent periods of time. Generally speaking, if there is a negative cash flow taking place at any period of time, a net negative cash flow taking place in the future, in addition to the initial negative cash flow, then you would have a situation of a non-normal cash flow pattern, and you will have multiple IRR values. Now, we mentioned that both of these values are incorrect, and to come up with the correct value of IRR, you use the modified or MIRR formula. The MIRR formula requires you to separate the cash inflows and the cash outflows. You lump the cash inflows and you compound them to the future, the final point in time where the project will end, and you lump the cash outflows and you discount them to the present. And then the MIRR is that rate at which you can discount the future value of the cash inflows and equate it with the present value of the cash outflows. In order to do this compounding and discounting of the cash inflows and outflows, you will use a certain required rate of return, which we will assume to be a safe rate of return or a risk-free rate of return. In Pakistan, you can take that value to be 10%. We talked about another special case, which was that of projects with different lifespans. We had two approaches to address this problem. One of them was the common life approach, and the other one was the EAA, or equivalent annual annuity approach. In the case of the common life approach, you take the least common multiple number of years for the life of all the projects. So in the case that you have one project with a lifespan of 2 years and another project with a lifespan of 3 years, you would have to come up with a combined common lifespan of 6 years, and you would replicate the cash flows of each project the required number of times to completely and exactly fill the 6-year period. Then you would calculate the net present values for each project on the common lifespan, and whichever project has the higher net present value would be the one that is selected, and that is the project that you should invest your money in. The other approach was the EAA approach, And in that, we simply multiply the simple net present value by an EAA factor. That factor is 1 plus I to the n divided by 1 plus I to the n minus 1. And that will give you what the implicit annual annuity value for a project with a certain net present value is. Then you can compare the annual annuity value of one project to another, and whichever project has the higher annual annuity value is the one that should be selected. The criteria of common life and EAA are consistent, so they will give you the same ranking. We then spoke about the advantages and disadvantages of projects with long and short lifespans. We mentioned that a project with a very short lifespan has the disadvantage that you are not certain about what cash flows to expect after the project ends. Because the project will end quickly, you might be forced to reinvest your money in a very low-yielding or low rate of return investment like a PLS account in a bank. Similarly, if a project lifespan is very, very long, you miss out on the opportunity to replace your equipment and your assets with newer equipments and assets that are more state-of-the-art, that can improve the quality of your product, the speed of your manufacturing, and generally improve the competitiveness of your business. We closed by emphasizing that so far we have not talked about capital budgeting in the context of a limited budget or a budget constraint. In the following lecture, we will talk about capital rationing, which is basically capital budgeting with a constrained budget or a limited budget. And we will study the concepts of budget utilization and IRR and NPV in that context. I would now like to close the material for this lecture. I'd like to emphasize, please, to kindly go over chapters 9 and 10 in Financial Management Theory and Practice by Brigham and Gapensky, and also to go over the homework assignments and practice problems to improve your understanding of the concepts that we have talked about in this lecture. Thank you very much for your kind attention and patience.